We're going to take a look at some problems with related rates. And let's just get started. The first few problems we're going to look at are just working with how do we take the derivative with respect to time. We've been so used to taking the derivative with respect to x that this may be new for us at this point in the course. So looking at problem number one, it tells me the radius and the area of a circle are related by this formula. That formula shouldn't be too new for you. Probably saw it in like a geometry class. But we want to take the derivative here so we can show how dAdt relates to drdt. So what we're going to do is take the derivative with respect to time. Beginning with the A, meaning area, we'll have dAdt. That simply represents the derivative of the area with respect to time. Now the pi is a constant, so actually it's a coefficient, so let's put it there in front, and then we'll take the derivative of r squared. So the derivative of r squared would be 2r times drdt. And I want you to think of this r squared as a chain rule, right? We're taking the derivative of something squared, which would be 2 times the something, and then we're taking the derivative of the inside, which would be the drdt there. Let's take a look then at the second problem, which is very similar. It's asking us for the how does dsdt relate to drdt? And we're given the surface area of a sphere formula. This one may not be as familiar to you, but we are definitely going to use it quite a bit in our course. So let's go ahead and take the derivative then of ds dt. That would be the derivative of surface area with respect to time. We've got our coefficient again of 4 pi. And now we take the derivative of our r squared. That would be 2r times drdt. And again, this is good practice for what we're going to do with related rates. So let's continue on then. We're told that the radius, height, and volume of a right circular cylinder relates by this formula. Again, that one should not be unusual to you. You probably saw it again in a geometry class. We're going to use this to answer 3, 4, and 5. Now in question 3, we're saying how does dVdt relate to drdt if h is a constant value? So we can think of h like a coefficient when we take the derivative. So we'll have dVdt equals pi h, because remember h is constant, so we don't have, the derivative of it is just going to be with the coefficient. Now we take the derivative of r squared, which again would be 2r times drdt. Let's do the same thing with number 4, except this time r is constant. So we have dVdt. We have pi r squared as our coefficient since r is constant. And then we have dhdt when we take the derivative there. So depending on which one is constant, that lets us know which one is the coefficient. Look at number 5. Number 5 says, how does dVdt relate to drdt and dhdt if neither r nor h is constant? So this is going to require a product rule for us. So I would do dVdt equals pi in front, and then let's work our product rule. Product rule is the first times the derivative of the second. The derivative of h is dhdt plus the second times the derivative of the first. And this is the derivative of r squared, which would be 2r times drdt. So the difference here in these 3 problems is which one is constant, and then we can fix that one, or if neither one is constant, it forces us to use a product rule then. Okay, let's go ahead and look at the next few problems. Now, I noticed that we had a problem 5 before, and now this one starts on number 7. Not sure what that's really about, but we're going to go with it. So look at this problem. We're told that the length of the rectangle is decreasing at a rate of 2 centimeters per second, and the width is increasing at a rate of 2 centimeters per second. When the length is 12 and the width is 5, find each of the rates of change. So friends, we need to go ahead and pick out those derivatives we're being given. We're told that dLdt, right, the derivative of the length, the LDT is decreasing. That means it's going to be negative. So we know dLdt is -2. I write my L's in cursive because I don't want them to look like ones, just so you know. And then I've been told that the width is increasing at a rate of 2. So that's dW dt equals a +2. And we'll use these for all three. So we're being asked for what is dA dt. So we need a formula that relates A, L, and W. Of course, that would be the area of a rectangle. So that's area is length times width. Neither one of these are fixed values, so we know we're going to have to do the product rule. That gives me dA dt equals first, which would be the length, times dW dt plus W times dL dt. And now we can put in all of these values. Remember, we were being asked for dA dt when L is 12 and width is 5. So that's going to give us all the values we need to plug in here. L is 12. dW dt is 2. W is 5. And dL dt is -2. So just a little bit of arithmetic here. And we get that dA dt is 14. Now watch your units because AP is going to require that you have units on it. Because it's area, we're going to go with square units. So centimeters squared per second. And we do it as a rate because it is a derivative. Now, continuing on with the same scenario, so we're going to now look at the perimeter. So we're looking for what is dP dt. So we need a formula that relates the perimeter with the length and the width. So perimeter of a rectangle would be 2L plus 2W. And now we take the derivative. dP dt equals 2 times dL dt plus 2 times dW dt. And notice in this one, I don't even have to plug in the 12 and the 5. I'm only going to use the derivatives here to get dP dt. So dL dt is -2 and dW dt is 2. So it looks like dP dt is -4 plus 4. dP dt is 0. There. And again, I want to put units for my rate, even though it's 0. Okay, one more with this rectangle scenario. And this time we're looking for the length of the diagonal of the rectangle. So I'm kind of a visual person, so I'm going to just draw a little scenario here, just so I can picture what's going on. I've got the width, I've got the length, and I'll just call this X for the diagonal, okay? So this question is asking us what is dx dt. So I hope you're seeing the Pythagorean theorem going on in this scenario. So you can use that as your formula to relate L, W, and X. And now take your derivative. So derivative of W squared is 2W times dW dt. The derivative of L squared is 2L times dL dt. And the derivative of X squared is 2X dx dt. Now let's plug everything in. Remember, this time we're going to go back and use the length being 12, the width being 5, as well as our dL dt and our dW dt. Say that fast twice. So let's plug those values in. The width was 5 and dW dt is 2. The length is 12 and dl dt is -2. Now, I don't know x, okay? But if I know, and I'm just going to draw a triangle over here, if I know these are 5 and 12, can I figure out what x is? Well, sure, I can do Pythagorean theorem over here on this side. Or you may be thinking, ooh, 5 and 12 go together with a Pythagorean triple. And you may have been able to say, oh, then the hypotenuse had to be 13. You'd be right. Pythagorean triple, 5, 12, and 13. They go together. And so we'll put 13 in there, and I've got dx dt that I'm looking for. Okay, let's solve for dx dt then. I've got 2 and 2 makes 4, and 5 is 20. 2 and 2 makes 2 and -2 makes -4, and 12 makes -48, and 2 and 13 is 26. So that gives me -28, and then we can divide by the 26. That'll give me, let's see, we can reduce here, right, by 2. So it looks like dx dt is going to be -14 thirds. Now, this is not a square, this is not an area, this is a length. So we're going to do it as centimeters squared for dx dt in this problem. Let's switch gears next to look at a sphere. So we're told that a spherical balloon is inflated. That word inflated is important. It's telling us that the balloon is getting bigger, and it's being inflated at a rate of 100 pi cubic feet per minute. Watch the units here. They're telling you that this is the volumes rate, dV dt. Now, because the balloon is being inflated, we know that volume is increasing. Therefore, volume should be positive. So we're going to leave it as a positive. Number 10 says, how fast is the balloon's radius changing? So this is asking us for drdt when the radius is 5. So we need a formula that relates volume with radius, and that's the volume of a sphere. If you don't have the list of formulas, I did this lesson video earlier. I'll link it below so that you can get the list. I have a really nice comprehensive list of the formulas that you need to know for the AP Calculus exam. So that would be a nice one to have. And this one's on that list. So now we'll do, take the derivative, dv dt equals your 4/3 pi, those are coefficients. So we put them in front. Now we take the derivative of r cubed, which would be 3r squared times dr dt. Now, time to plug everything in that we know. We know dv dt, 100 pi. And we know that r, we are told, is 5. So we'll put that in. And then it's a matter of solving for dr dt. Let's clean it up just a bit. I like the 3's canceling there. Then I've got 5 squared, which is 25, times 4 gives me 100 pi times dr dt. Then I'm going to divide both sides by not by dr dt, by 100 pi. And I've got that dr dt is 1. So then you ask yourself, 1 what? What are your units here for the radius being just a length? It would be feet per minute. Okay, look at question 11. Staying with this same spherical balloon, how fast is the surface area increasing when the radius is 5 feet? So this one's asking me for ds dt. So we need a formula that relates surface area to the radius or the volume. Well, the only formula I know, and it's on my list again, don't forget I link it below, surface area relates the volume in a sphere. So now we can take the derivative of this. So we get ds dt equals 4 pi times, the derivative of r squared would be 2r times drdt. Now let's plug in what we know. From our previous problem, we know drdt, right? We can use that is 1. So we'll plug that in. That's one beauty of the AP exam is that when you get on those free response portions, you're going to use the answers from part A and B to answer C. And so you can do that in this case as well. So I've got ds dt equals, and let's just multiply this. 4 times 2 is 8. 8 times 5 is 40 pi. Now this is surface area, so we've got to do square units per minute here. It's a good classic problem with a sphere, so you can see that we use dVdt, drdt, and dsdt. All right, next let's take a look at the conical tank. So beware with cones. A lot of times they do require the product rule. So I always encourage that you draw a picture so that you kind of get an idea, even if you're not the world's greatest artist, and I'm not either. You definitely want to get an idea and a feel for what this looks like. And I refer to it often as the snow cone, okay? So you've got 10 feet across the top, which a lot of times our formulas are based on the radius. So while it may be 10 feet across the top, that's really telling you that the radius is 5. And that's of the full snow cone cup, the cone, right? And we're told that the height of the cone is 12. If water's flowing into the tank, that's a key word, flowing into the tank at a rate of 10 cubic feet per minute. Watch the cubic feet. That's letting you know that dVdt is a positive 10. Now it's positive because it's flowing into the tank. Then we want the rate of change of the depth of the water when the water is 8 feet deep. So what that means is that you have a snow cone cup here, but you also have snow cone juice, right? And it has a radius that's changing, and it has a height that's also changing. So we need a formula that relates volume, radius, height for a cylinder, that is pi r squared. I'm sorry, for a cone, that is 1/3 pi r squared h. I was thinking cylinder, but needing to get cone. Now, here's my problem. We're asked for the rate of change of the depth, so we want to know what is the HDT. Now, the problem here is that we don't have anything about drdt. So what we can do is I want you to see that we have a proportion between the radius of the snow cone juice and the radius of the full snow cone cup, the height of the snow cone juice, and the height of the snow cone cup. So let's set up a proportion. We've got the radius of the snow cone juice is to 5, as the height of the snow cone juice is to 12. Now I'm going to solve for the radius here by multiplying by 5. And the reason I'm doing that is so that I can get the radius by itself. And what I'm going to do is use substitution to get rid of to eliminate the radius here. Now, friends, notice that I have not done any calculus at this point. Okay, this is just straight up algebra to get rid of one variable. Sometimes we can do the algebra to make the calculus easier. And in that case, if it makes the calculus easier, I definitely want to do it. Let's see, 3 times 144, let's see, 2 and 3 and 432 pi, and I should have a 25 there, h cubed. Now, again, haven't done any calculus because now that I only have height and volume, I have made the calculus a lot easier. So I'm going to take my derivative now. dv dt equals 25 432 pi, those are my coefficients, right? Times 3h squared times dh dt. Okay, now we need to find dh dt. We know dv dt, so we can plug in 10. We know h is 8 because that's the moment we want the derivative. So I'm going to plug in 10 for dv dt, 432 pi times 3 times 8 squared times dh dt. So let's clean up this right side now, okay? It's kind of a hot mess. So I've got 3 times 64. I'm pulling out the calculator here. 3 times 64 gives me 192. And then 192 times 25. Whoa, that's a large number. That gives me 4,800 over 432 pi times dh dt. And let's see. It's not going to divide evenly, so I'm going to go ahead and flip it and multiply. So I've got 4,320 when I multiply it by 10 over 4,800 pi. Now it gets a little smaller when I can eliminate those zeros. Now I've got 432 over 480. And let's see, I probably can divide by 8. No, yes, 8 at least. So that'll give me 54 over 60. And then I can go one more time dividing by 6. I'll get 9 over 10 pi. And then my units, right, this is h, so they're going to be feet per minute. And that is dh dt. All right, the cone, always a fun one because we have to do, most of the time when we do a cone, we have to use the similar triangles, okay? So let's take a look at the classic ladder problems. This will be a good one. A ladder is 25 feet long. Notice not changing. That ladder is not changing length. The base of the ladder is being pulled away from the wall at a rate of 2 feet per second. Use this information for 13 through 15. So gonna draw a picture, of course. Ladder is a fixed length. And friends, you can call these variables anything you want. I'm just going to call it x and y. Makes it real simple. We're told the base of the ladder is being pulled away from the wall. That means that dx dt is getting bigger. So dx dt is a positive 2. And so look at what number 13 is asking us. Number 13 is saying, what is dy dt? What is dy dt when x is 15? Okay, so I need a formula that relates x and y. Hope you're seeing the Pythagorean theorem here. X squared plus y squared equals 25 squared. At this point, I'm ready to take the derivative. So I've got 2x times dx dt plus 2y times dy dt equals 0. Now, classic problem that students miss on the AP exam is they just translate that 25 squared there. Instead of the derivative of a constant is still 0. Now, let's plug in what we know. We know x is 15. We know dx dt is 2. We don't know why, but we could find it, okay? If x is 15, draw a little triangle over here. If x is 15, we need to find y. So we can do Pythagorean theorem. Now, if you're thinking that's a Pythagorean triple, you're right. It is. So you can see that y turns out to be 20. So we can put 20 in there. Then let's go ahead and solve, right? 2 times 15, 30, times 2, 60. 2 times 20, 40, times dy dt. Move our 60 over. We get 40 times dy dt equals negative 60. Then I get dy dt equals negative 60 over 40, or negative 3/2. My units here are feet per second. Now take a moment and look at what we got, a negative for dy dt. That means that dy dt is decreasing. Does that make sense when this ladder is being pulled away from the wall? Yes, it does. Okay. You want to mentally check that to make sure your calculations should mirror actually what's happening in the problem. If they don't make sense, we did something wrong in the problem. So always mentally check that. All right, number 14 then says, consider the triangle formed by the side of the house, the ladder, and the ground. Find the rate at which the area of this triangle is changing when the ladder is 9 feet from the ground. So this one is asking us to stay with the same scenario, but I want to know what Dhdt is when the ladder is 9 feet. So that's when x equals 9. We need a formula that relates the area to x and y. So that formula for the area of a triangle, 1/2 x times y. You remember it as 1/2 base times height? Okay, well, x and y are just my base and height for this problem. So when we take the derivative of this, I have to use product rule. So that's dAdt equals 1/2 first times derivative of the second plus the second times derivative of the first. And now let's put in everything we know. We're looking for dAdt. We know x is 9. We know dy dt is negative 3/2. We know y. Let's think about y. If x is 9, we need to find y. So let's do our Pythagorean theorem again. This one doesn't come out to be a Pythagorean triple. That's okay though. We'll subtract 81, so that'll give me 544. I'm just going to leave it as the square root of 544 for right now. It'll make it a little bit easier in my problem. And then dx dt, of course, was 2. And then let's just do some arithmetic here, right? I've got 1/2 negative 27 over 2 plus 2 square root of 544. Let's distribute that 1/2. I think it's going to make it a little bit easier for us. So that'll give me negative 27 fourths plus the square root of 544. And this is dAdt. Now, if we want a decimal, we most certainly can get one. Let me pull up my calculator here. And I'm going to put this value in here. So I've got negative 27 fourths. And then plus the square root of 544. Press enter. We get 16.5 574. Remember, AP requires 3 decimal places. And this is in area, so we're going to have feet squared or square feet per second as our units here to work with. Okay, let's switch formats back so that you can, we'll look at part C. If we need to come back to my calculator, we definitely can do that. Sorry, not part C, part 15 says, find the rate at which the angle between the ladder and the ground is changing when the base is 7 feet from the wall. So remember our diagram we had? We had 25, we had X and Y. We want to find the rate at which the angle between the ladder and the ground. That's very important that you identify the correct angle. And for that, that's between the ladder and the ground. That's this angle. And we want to know it when X, so we want to know what d theta dt is when X is 7. So let's rewrite a formula that relates X and theta. I hope you're thinking trig function, right? I'm relating those two. That's going to give me cosine of theta is X over 25. Now, for our purposes of the derivative, it might be a little bit easier for us to think of this as cosine equals 1 over 25x. So let's take the derivative now. The derivative of cosine is negative sine theta times d theta dt equals 1 over 25 times dx dt. Now, in order to find sine of theta, we'll need to find out what y is when x is 7. So let's see, I've got y squared plus 7 squared equals 25 squared. So y squared plus 49 equals 625. So y squared equals 576. So y is 24. So sine of theta, actually negative sine of theta would be negative 24 over 25 times d theta dt equals 1 over 25 times dx dt. Remember, we were told that was 2. So now I've got negative 24 over 25 times d theta dt equals 2 over 25. And now you can flip and multiply the negative 24 25ths. So you got 2 over 25 times 25 over negative 24. So d theta dt is negative 1/12. Watch your units here. It's radians per second. Radians because it's an angle, and then seconds because that was our unit of time in this particular problem. All right, let's switch over to look at question number 16 then. We have water flowing at a rate of 50 cubic meters per minute from a conical reservoir. That's important. That's telling us dVdt is a negative value. It's negative 50. The radius of the reservoir is 45 meters. The height is 6. That's your full snow cone cup, right? So your full snow cone cup has a radius of 45 and a height of 6. Okay, how fast is the water level rising? So this is asking us, what is dHdt when H is 5? So think about your not full, right? Your snow cone juice only comes to this level, right? And it has a radius of 5. Nope, it has a radius we don't know. And it has a height we don't know. So you can set up your proportion. You've got the radius of your snow cone juice is to 45. as the height of your snow cone juice is to 6. We're going to be trying to use the volume of a cone formula, 1/3 pi r squared h. And we're going to get rid of the radius. So let's solve for the radius here by multiplying by 45. So that I get, let's see, we can divide both of those by 3. So I get 15/2 h. And I'm going to make that substitution in my formula before I take the derivative. So I've got 15/2 h squared times h. Now take a moment and clean it up before you take the derivative. So you've got 225 over 4 h squared times h. Reduce the 3 and the 225. That'll give you 75 pi over 4 h cubed. And now you're ready to take the derivative. So that'll give me dv dt equals 75 pi over 4 times derivative of h would be 3h squared times dh dt. Now plug in everything you know. Okay, you know dv dt is negative 50. You know h is 5. So I've got negative 50. 75 pi over 4 times 3 times 5 squared times dh dt. Okay, so I've got 25 times 3 gives me 75. Let's see, 75 times 75 gives me 5,625 pi over 4 times dh dt. And then flip and multiply. So I've got negative 200 over 5,625 pi. And then let's see, that'll also reduce by 5. So I've got, let's see, I think it'll reduce by 8. No, it won't reduce by 8. So we reduce by 5, I've got negative 40 over 5,625 divided by 5 gives me 1125 pi. Don't lose my pi on that, right? I think I can go by 5 one more time. And that gives me negative 8 over 225 pi. Don't forget your units, which are meters per minute. There. Okay, now look at 17. 17 says, how fast is the radius changing? So now that we know dH dt, we want to know what drdt is. So when we eliminated r in the previous problem, that was fine. It helped us get dH dt, but now we've got to go back and leave it in. And let's do a product rule. I'm going to leave the pi over 3 in front here, and then I'll do my product rule. That's first times derivative of the second, that's dH dt, plus the second times the derivative of the first, so times r squared would be 2r times the r dt. And let's plug in what we know. We know dv dt is negative 50. I don't know what r is. I only know what h is. But remember, we have a relationship between, and that should be an r, friends. We caught that. Good. We have a relationship between r and h. We know that r is 15/2 h. So if h is 5, I know that r is 75/2 because I can do 15 times 5 and then divide by 2. So I know that r is 75/2, and we've got to square it. dH dt, we found out in the previous problem, negative 8 over 225 pi. Plus h was 5 times 2 times r, 75/2, and we're looking for dr dt. Okay, it's going to get A little bit sloppy, but we're going to try to hold it all together. All right, let's do a little bit at a time. I've got 75 squared, and then I'm going to multiply times -8. That'll give me -45,000 on top here. And then I've got 2 squared is 4, and then times 225 will give me 900 pi on the bottom. Then here, oops, forgive me, that should be there. I've got the 2's canceling, so I've got 5 times 75, and that gives me 375 drdt. Okay, I would probably distribute the pi over 3 now. Let me cancel these first. Okay, makes that a little bit easier. When I distribute, the pi's are going to cancel, and I'm going to do 450 divided by 3. That's going to give me -150. And then distribute it here. 375 divided by 3 gives me 125 pi times drdt. Ooh, that cleaned up a little bit better, right? So I'm going to add the 150. That gives me 100 equals 125 pi drdt. Then I'm going to divide by that 125. It's going to give me 4/5 pi. And my units are meters per minute. So good cone problem there to work through. All right, keep working along here on number 18. A man 6 feet tall walks at a rate of 5 feet per second towards a street light that is 16 feet tall. The man's height isn't changing, not in any good speed. And your street light's not changing. So this is my street light. And it's 16 feet. And the man is traveling, and he is 6 feet. And you have your street light, right, that's casting a light, and so you have a shadow behind the man. Okay. I'm going to label some things just that are changing. So I'm going to make this length of his shadow X. I'm going to make his distance from the street light Y, that's changing as well. Okay. The man walks at a rate of 5 feet per second toward the light. So that means that this distance here, this dy dt, is decreasing as he walks towards the light. So that means that's a -5. It's asking for what is the rate, what rate is the length of his shadow? So it's saying what is dx dt when y is 10, when he's 10 feet from the base of the light. Now, I'm hoping you're seeing the 2 nested triangles here, because we're going to need them to set up our similar triangles. So I've got that x is to y, x is to xy, x plus y, as 6 is to 16. Now, what I'm doing is I'm saying the small triangle is to the big triangle. That's why I had to do x plus y. Now, again, it's probably easiest if we simplify these the fraction first by like cross multiplying. It makes it a lot simpler when we take the derivative. Now take your derivative. You've got 10 times dx dt equals 6 times dy dt. Plug in what you know. You know that dy dt is -5. And so 10 times dx dt equals -30. So dx dt is -3. And my units here are feet per second. Feet per second. All right, friends, thanks for sticking with me so far. We've just got a few more problems to look at for these related rates. Remember, practice makes progress. So every bit of practice you're doing with these related rates is going to help you do very well on the AP exam. And I will say this list of problems is comprehensive. So you're getting one of every type, which is always good. Number 19 asks us about the volume of a cube. Oh, tongue-tied today. And it's told it's increasing at a rate. So we know dVdt equals 24, and it's positive because it's increasing. And each edge, dEdt, is increasing at 2 inches per minute. So it says, well, what is the length of the edge when this is happening? So we need a formula that relates volume times edge, which we know in a cube, we would multiply length times width times height, where all of those are the edges, they're the same. So the volume is e cubed. So take your derivative, dV dt equals 3 times e squared times dE dt. Plug in what you know. You know dV dt is 24. We don't know E, but we know dE dt is 2. So 3 and 2 is 6. And so you know E squared is 4. So that lets you know that E is 2 inches here. Why did I not consider the negative? Because we can't have a negative edge on this cube. Let's take a look then at number 20. If the volume of the cube is increasing at a rate of 24 cubic inches per minute, we've got dV dt again is positive 24. The surface area, ds dt, is 12. What is the length of the edges? Ooh, okay. So we need surface area formula. I've got that the surface area, I know in a cube there are 6 faces, right? And they're all squares. So that would be edge squared, right? Okay, now if I take my derivative, ds dt equals 12e times dE dt. ds dt is 12. And so I've got that E times dE dt is 1. Now, I haven't been told I can use the value from the previous problem, so I'm not going to do that. Instead, let's try to work with the volume now, since we were told that. Remember, the volume was E cubed. So dV dt equals 3e squared times dE dt. And we're told the dV dt is 24. Now, friends, for a reason, I'm going to write it like this. I'm going to write E squared as E times E, because what I want you to see is that we were told E times dE dt, or we found that that's 1. So I'm going to make that substitution. I got 24 equals 3 times E times 1, because we know E times dE dt is 1. That lets me find out that E is 8 inches here. That's tricky, okay? And it has to happen because it told me dV dt and ds dt. All right, last problem. We're almost there. Okay, on a morning when the sun is passing directly overhead, the shadow of an 80-foot building on the level ground is 60 feet long. At the moment in question, the angle the sun makes with the ground is increasing at a rate. Okay, so let's draw. Here's our building. I oversimplify our building, trust me. So our building is 80. Yep, our building is 80 feet tall. We've got the sun here, and we've got a shadow. Okay, and then we know that we've got the angle the sun makes with the ground. So that's this angle. And we want to know what is the length of the shadow decreasing, dx dt. when x equals 60. Okay, I'm probably going to use tangent here. So I've got tangent of theta equals 80 over x. Now take your derivative, derivative of tangent, secant squared times d theta dt equals, think of this as 80 times x to the negative 1. So you got negative 80 times x to the negative 2 times dx dt. And let's plug in what we know. Now, we know when x is 60, this is 80, this is 60. Hope you're seeing that Pythagorean triple again, right? This is a 3, a 4. They're all divisible by 20, right? A 3, a 4, a 5. So this would have to be 100. Check the Pythagorean theorem if that didn't make sense there. But the secant squared then would be 100 over 60. Or if you reduce it or make it easier, that's 5/3. We told d theta dt is 0.27. X is 60 squared dx dt. Now, because they used a decimal, that leads me to believe that we can use our calculator. So I'm going to switch us over to use my calculator on this one. I've got, I don't really like that 5/3 part, but let's see what happens. I've got 5/3 being squared. And then I'm multiplying by 0.27. Oh, good, that came out nice. Then I've got 0.75. And then I've got negative 80 over 60 squared. That did not come out nice. So I'm going to do it as a fraction. By what I did there, friends, math inner, right? That's how I change that to a decimal. Okay. And I might, just for simplicity's sake, change that 0.75 to positive 3/4. Might make it a little bit easier. So I can do 45 times 3. And that gives me negative 135 over 4. And that's feet per minute for dx dt. All right, I hope that helps with our related rates. Of course, as always, if you have questions or comments, please leave them down in the comments below. I'd be glad to help with anything I can. Bye for now.